Hi there. So I'm going to go over power in AC circuits. I'll show you the voltage triangles and how we derive power from that. I'll quickly go over the equations that you need, including active, reactive and apparent power, the angle here, and also the power factor in this video. Alright, so you should be pretty much comfortable with the voltage triangle here. In case you're not, I'll just quickly go over VR here. We're taking the current in this series circuit as the reference. So just be aware that the current is in phase with the voltage across the resistor. There is no phase difference there. So we're taking the current as the reference, and VR, which is in phase, will be along this horizontal axis. Remember, we're talking about complex impedances here. So we're in the real and imaginary axis, the Argand diagram. These are vectors. We've got the voltage drop across the inductor, the phasor here, and we've got the voltage across the supply voltage. And then we've got some phase difference here, and that phase difference is the difference between the supply voltage and the supply current. Again, remember, supply current in phase with the voltage across the resistor. So how do we get power triangle from this? Well, first of all, realize that there are a number of ways. If you remember back into your DC circuits, power was... Oh, if I just go onto the pen there. So power was equal to I squared R, which was V squared over R. And that power there was all active power. So all the power was being dissipated by the resistor R. So it's very similar here. We can have the active power as a product. So let's say we've got VR down here, and we'll have IS as well. And I tell you what, I'll do IS in red here. So IS, so VR times IS. We've also got VR squared, and that's divided by the resistance. So VR squared over the resistance. And that there will give us power. Okay, so what about VL? We have a 90-degree phasor here. Well, what we'll do is we have VL. What is the reactance of that? That's XL. Well, I should have done that on a different triangle, sorry. We'll multiply that first of all by IS. And then we've got VL, and that's divided by XL. I should square it. So VL times IS and VL squared divided by XL is what we call reactive power. I'll stick with green for this. And finally, so VS times the supply current, that's the same as VS squared divided by the overall combination of the resistance and the reactance, which we call the impedance. And that we call the apparent power. So we've got P is active. I'll put this, I'll go for this colour. Active, we'll go reactive, and we've got apparent. I'm not very good at keeping it on the screen here, am I? So we've got apparent. And this is easy to remember for me, because where you've got reactance, you have reactive power. So when you take in the voltage drop across the reactor, which is either a capacitor or an inductor, you're going to get either positive or negative reactive power. And active power is the heat loss that that is dissipated in a resistor. And apparent power is the vectorial combination of these. So we've derived the triangles. Let's now go into the equations. So let's first of all this one, but for AC circuits. We have power, and that's active, remember. And that is equal to the voltage supply times the current supply, because that there is S here. So S is the voltage supply times the current supply. And so basically what we're saying is we're taking the apparent power, S, so that's Vs times Is, and we're going to go cosine of the angle. And that's just SOHCAHTOA here. So we're looking for P, active power, and what we're doing is VSIS, apparent power, times the cosine of this angle. It's just SOHCAHTOA there, trigonometry. Okay, so let's go to reactive power. Q, and I'll just make it clear, I'll put reactive. Remember, this is the power that's been consumed / generated by the inductor with the expanding and collapsing magnetic field. So that there is VSIS sine theta. And again, SOHCAHTOA. VSIS, that's the apparent power, times the sine of this angle. But hey, I got some rogue triangles down here. Let's get rid of them. And now what we're going to do is we got to have an expression for S, right? Because S is a combination of these, a vectorial combination. So we'll go apparent. Let's put that, and S is equal to a combination of these. Remember, we're in the complex domain, so we'll go P plus JQ. And that is also the square root of P squared plus Q squared, and that's with an angle 30 degrees. Alright, so what is this theta, I wonder? Or phi, I think actually I've denoted it, Greek letter phi. Well, what we're wanting is we're wanting the phase difference between the voltage Vs and the supply current Is. So there are two ways of doing that. So if you have Vs as your, sorry, that's not a very good diagram, but say this is a phasor and we have Vs there. Hang on a sec. So yeah, so say we've got Vs there and we've got a supply current, we've got Is. So Vs here is our reference. So you usually find this. So Vs 0 degrees. We got Is at 90 degrees. From Is you'll have VL, and that's VR as well, don't forget. Is VR. So here what we want is we want the phase difference between Vs and Is. So we got a phase here. We'll give it red, we'll give it phase of I. And theta is equal to the phase of the voltage, which in this situation, because we've got the voltage as the reference, it'll just be 0, and the phase current. And the phase of the current. So if we put some numbers to this, so say for example the phase of the current was negative 10 degrees, shall we say. So we go, the phase of the current is equal to minus 10 degrees. The phase of the voltage in this situation is 0 because it's the reference. Then phi would be equal to 0 minus 10. So in this case phi is equal to 10 degrees. Bit of a weird one. Alright, but how about if you had this? So we got VL and we got VR and we got VS. Well, here Is is the reference, and the voltage over the resistor this time is the reference. So what we got the voltage, so we got V, and here the voltage, the phase of the current is 0. So this time if we say that the voltage is 10, say that's 10 degrees, just to keep it in line with this. So we got the phase of the voltage is equal to 10 degrees. Then phi is equal to, what was it again? It was the difference between the voltage, the phase of the voltage, and the phase of the current. So here it will be 10 degrees minus 0, which is 10 degrees. So why is that relevant? Well, this theta here, this tells us a lot about the power factor and the angle. So here we've got the active, reactive, and the apparent power, and all of these are functions of the angle phi, as to all these triangles. And this is important for telling us about the power factor. So the power factor, this is the ratio between the active and the apparent power. So basically, in the demonstration in class, we had a pint of beer, or it was half pint in class. If I can draw a beer, we'll just say, there we go, that's the beer there, cross hatchet, and that's the head. So here the head is the reactive, this is the active, the actual liquid that we can drink, and those two combined, well, they're both S. So what we want to do is find the ratio of active or drinkable beer to the total volume, which is basically what this power factor is telling us. So we can take the ratio of P over S. So what is P? Well, if you remember back up here, Vs Is cos theta so we got Vs Is times cos theta, and that's divided by S, which is Vs Is. Well, these cancel out, and what we're left with is cos theta. So the power factor, we'll just say PF for short, is equal to cos theta. Or if you've got a power factor and you want to find out what the angle is, where you do simple algebraic manipulation there, and we got cos, the inverse cos of the power factor is equal to theta. Hopefully with a few examples this will become clear as to why this is important.